start at this point. So to kick it all off, welcome. We're controlling the power of SaltStack across. That's a really big title. We're going to talk about how we and Dun & Bradstreet use SaltStack, and we're doing so under a capital E enterprise kind of company. So we're not talking about a single app. It's just lots of teams, lots of silos, and how Salt helps us with some of those problems. So really quick about me slide. I'm a guy who's done some stuff. That part's fine. I mention all of this because I have a GitHub URL here with GitHub links to some of the stuff we'll be talking about. So you don't have to worry about taking notes or on really tiny text on PowerPoint slides. You can look this up if you want to later. Subnote, I also wrote the SaltStack Jenkins plugin. And so if anyone has problems or anything about that, you know where to find me. All right. So we're going to talk about some topics that I think are pretty relevant. I live in Dublin, Ireland, and flew in for the conference. Point being, I haven't gotten more than 5 hours of sleep over the past 2 days. So if you have any questions, please shout them out because I would really like the interaction to keep me personally awake. Also, if some topic is just so interesting that we have to talk about it for a while and don't get to later ones, that's also totally okay with me. So feel free to raise hands, shout out, whatever you need. All right. So talking over our Salt setup with GitFS and all, the Zabbixy stuff we're doing, the AWS stuff we're doing, how we're using Jenkins, and then finally some Vault. So to kick it off, let's talk about some exciting background information. So Salt. As you're probably aware, being at a Salt conference, Salt's the kind of product where if you have some system out there, you can put the Salt minion on it. So great, we have a Salt minion on a host. That Salt minion talks into the Salt master over a hub subscribe bus. So whoop, talks in. That's important for firewalling rules, and this is one of the reasons that makes Salt kind of advantageous for us to run in a big enterprise company, because that simplifies our firewall rule set quite a bit, as we'll get to in a little while. But in short, we have scalable infrastructure in a unidirectional way where things talk into a Salt master. Our Salt master then speaks back to the host. Based on information about that host, can then provision that host and the stuff we need on there. So the specifics of what is on the slide aren't really all important, just that in any big company, you probably have a policy that says something to the effect of nothing touches a system without it going through configuration management. Makes sense. So on top of that, we can also manage what Salt is doing through Git. So we can ensure that everything that Salt is installing that environment is managed through a Git workflow. And that's nice because that gives us all the advantages of a Git workflow for operations-y, sysadmin kind of work. So this is where you get into the configuration management tool sets and all the advantages that it provides. We can do things like track change on our environments, have proper commit messages, the general development workflows that Git gives you. Great, we have that with Salt as well. That also, because we're using GitFS for a bunch of these workflows, that makes the Git repo itself authoritative for what goes out into our environments, so that as changes get made, that those changes get propagated, so we have some change control and tracking on what those changes were and so on. Awesome. But Salt has another advantage. It has an event bus. And that event bus gives us the ability to then leverage that event bus to do some stuff. So in our environment, that means that we will, because we spun up this host, and because we added this NTP and Apache and whatever states to that host, we can then monitor and ensure that all the stuff we did on that host is tracked. So because we spun up that stuff because we spun up this infrastructure with these states, let's ensure that we're monitoring all of those states as they were applied. So great, now we've added our host into our monitoring system and so on. In addition to that, we can also control some of the CMDB-like functionality and do the same thing with an inventory service and ensure that it's populated as appropriate as well. So since Salt has the knowledge of the grains off that individual host, it might have knowledge of our AWS environments, whatever it is, we can ensure that information is recorded and tracked. And this is what gives you some of the advantages of a CMDB-like system, even if you're not even using inventory services or CMDBs, because Salt itself gives you the ability to query a lot of that information hot. But if you are using a CMDB, I now have an authoritative way to update that CMDB and ensure that it's in a consistent state. So that's pretty good. And then as far as lifecycle management goes, if I kill off an infrastructure, I can also send a message to our various services and let them know, hey, by the way, clean up. So if we need to remove a machine from Active Directory, if we need to remove it from monitoring, whatever the thing is, we have the Salt event bus that allows us to do so. And that's the thing that we're actively using at the moment. Very, very handy. Salt, not so bad, right? So let's talk about AWS for a little while, because that also is involved in why some of the subsequent stuff we'll be talking about. So in our environment, we have many, many development teams across the world under different silos in different places. And so I don't have just one application to manage. I might have hundreds. And so in that kind of environment, we need a way to scale out what it is we're going to run so that team A can affect team B. We also want to make sure that our AWS environments are scaled so that we have a proactive security model, but possibly even more importantly, we have compliance and security concerns on top of all of this. So our system for managing a bunch of that was to split up our AWS environment from maybe a monolithic or a handful of accounts or VPCs into an account per application per environment. So in this case, we have this ES micro dev, so we have this platform enterprise services, they have a microservices account. Well, here they have a dev instance for that platform. Well, we'll also create a staging and a production for them as well. So these are 3 separate AWS accounts. So this means when an auditor comes in and they say, hey, does user Joe have access to prod, we can just easily scan the prod account and then tell you right away, yes or no. And that's a whole lot easier than us going through all of our security groups and ensuring that we didn't accidentally make something too permissive that one time, and thus the auditor will come in and ding us later. So in an effort to simplify all of our security concerns, let's fully segregate these environments. This also will get into the provisioning of why that helps us as well in a moment here. All right, so we have our AWS accounts. We have a Git repo where our application team probably creates some application code. And that's pretty good. That's generally what we do in software development. That works out fine. The way we deploy into these environments, though, is that we want to make sure that we manage the infrastructure of what goes into those environments as well. So in our case, that means that we run some Terraform code to provision out these AWS environments. And I want to pause here for a moment to describe our Terraform process because there were some learnings that occurred along the way as well. So we went through a few different ways through CloudFormation and through Troposphere for our AWS provisioning, but we ended up settling on Terraform because of its simplicity. The YAML files don't incorporate a whole lot of boilerplates. They're reasonably simple things to generate. It was reasonably simple for folks to wrap their minds around them. And initially, we had a problem with it, however, where Terraform writes out a state file. So what exists in your AWS environment is what actually exists there. And then separately, Terraform has its own internal concept of what's been provisioned there. So that means if you were to, say, apply Terraform into an environment and provision a thing, it wrote out a state file, and what's actually existing and what's in your state file are in sync and everything's fine. If someone were to manually later go in and change your environment, which I do not advocate and should not be done, but if it were to happen, now your state file is out of sync, and now you have some maintenance to either destroy what's there, recreate it, get that stuff incorporated into Terraform, whatever you have to do. So there's some maintenance and overhead there of making sure that Terraform knows about what's in the environment. Well, for us, that was kind of annoying, and so we ended up going down other paths. But after further investigation, we ended up turning that into a positive. So the way that we provision out these environments now is that the account itself is spun up. The VPC, the subnets, the logging stuff we're doing, some of the other things that we'll talk about, all of the components that makes that environment ready for use by one of our application teams is provisioned with Terraform, which means that we have our Terraform code that gets run, that writes out a state file someplace, so that later when our application teams have to provision their own apps into that environment, let's say it's an EC2 instance or whatever it is, rather than having to hard code the individual IDs for what goes into that environment, the VPC ID, the subnet IDs, and so on, they can instead import that existing state file from the infrastructure provisioning step itself and now just reference the variables. This now simplifies what the application team has to do. And this will be a pretty consistent drumbeat throughout this presentation of make sure you have a well-defined interface for all of your various teams. We have an application team whose sole focus is to get an application out there to solve a business need, to add some business value, or to satisfy customer value. We have an infrastructure team which is trying to have a consistent and known stable infrastructure. Those are not necessarily opposing views. We just want to make sure we have a good interface for those teams to be able to operate very nicely. In our case, that meant the infrastructure team writes out with Terraform what's going to exist. Our application teams can then depend on those state files existing in those formats in those places, which means they can now provision on top of what was done by our infrastructure teams. So cool, we have some Terraform. The Terraform environment is responsible for making sure that things are tagged appropriately and that Salt stuff is set up as you'd expect. The tags are a thing that we'll depend on in these environments as we go through them as well. All right. So that means we can now spin up our infrastructure. If we have our operations team or whoever that generated out the AWS account, they provision out the VPC, all the subnets, all that stuff. We then have, that's one set of Terraform, which is effectively not shown here. And now this Terraform references the applications team's code itself. So that as an application team spins up, let's say, this ELB and EC2 instance to run their app, they have some knowledge of what their app entails. They will codify that knowledge into this Terraform code. And alongside their application code, we can now keep our what the service requires to run on, as well as the application, and keep them in the same Git repo so that they're able to iterate in lockstep. So that means we've enabled a development team to be able to deploy their stuff to this dev environment. Pretty cool. We are compiling that application code, spinning up the Terraform, creating our application's infrastructure in the AWS environment, and deploying out that application code so that the development team is able to just see the results of updates to these Git repos in their environments without having to really bug anybody. So that means they're able to iterate. So cool, we have a version 0.1 of app, and they're capable of taking that through to see that it gets to version 1.0 of app, whatever it is. So at this stage, we're probably very confident we want to move this thing along through our pipelines. So the benefit of what we're doing here is that we've taken our application code and we have the infrastructure that the application code requires, and they're right next to each other. So that means we can then just run it again. So we can spin that same environment up in the staging account. And so the thing that was tested in dev that we decided to move into staging is the thing that was actually deployed to staging. You guys aren't applauding there, but I don't know if you ever worked in like a really big company, and that is freaking gigantic. That we are no longer trying to remediate what's in our environment. We're not trying to control what's in our environments by going through an upgrade path. We're able to provision what should be in our environments. And that declarative provisioning is amazing and not necessarily as easy to sell as you would think it should be all the time. So we're now able to run our, is there a question?
Yeah, so do you whitelist your environment when you do the Git app as a backend?
Do we whitelist environments?
Yeah, do you staging and production?
It depends on what we're doing for the individual. I mean, in Salt?
Yeah, in the Git app as a backend.
So at this stage, we're not necessarily invoking Salt, but by this stage, we would, generally the way we're running our Salt environments at the moment is that everything's under base. So everything's in master. So we have a consistent deployment. So what's in dev is the thing that will eventually be in prod. We want to make sure that for Salt, we have a different development pipeline than we do for the application provisioning pipeline. That if we provision out a dev instance, if that dev instance is called whatever app version 1.0, and we move that whatever app version 1.0 into production, it's the exact same whatever app version 1.0. And that's the secret sauce behind this, that I want to make sure that the thing that was tested in dev, that was moved into staging, validated in staging, passed over our QA whatever tests, and that's the thing that moved into production, that is exactly the same stuff that was previously tested. There shouldn't be any surprises through this pipeline. So at the moment, the Salt code is considered separate from this, that this is all production Salt by this point. Even though it's a dev environment, it's production Salt. And as described, we can move into prod. Yeah. All right. So I've described this process of provisioning Terraform, and one of the implications of this is how do we actually allow a development team to be able to provision a thing safely? So if we had a shared environment, I might have a user who does that provisioning process. So now my user has to have an IAM role or policy or whatever that allows them to act in this environment, and that means they're now potentially like a security risk, or maybe we have like a super duper security policy that only allows them to touch their one app, but there's actually a bunch of resources in AWS which are shared on the accounts or maybe the VPC, and so I can't really guarantee that a single deploy of app A won't affect a deploy of app B if we're in a shared environment. So that's one of the reasons why we got into different AWS accounts. But even easier than that was our provisioning process itself. So for that, we use Jenkins. So Jenkins is our CI pipeline and everything else. Well, it's also how we're going through a bunch of our deployments. So with Jenkins, we have an EC2 instance that lives in each of our AWS accounts. We run ECS on top of that. So this is Elastic Container Services, Amazon's Docker infrastructure. And on top of that, we run Jenkins agents. So for our Jenkins setup, the Jenkins master itself doesn't actually have any ability to do much of anything. It has no executors on it. It can't run any jobs. And it has no rights to do anything into an AWS environment except for spin up those Jenkins agents. So the workflow there for us is something to the effect of we have a Jenkins pipeline. That pipeline says whenever code is committed or whatever, kick off the pipeline, spin up a Jenkins agent into, let's say, the dev environment, which has a Java build environment, let's say. So we then spin up the Docker image that has the Java build environment. We copy over our Git code. We do our compile process of whatever it's configured to do. It takes the compiled artifacts, dumps it into Nexus, Artifactory, S3, whatever. And then after that, our deployment process is that the Java build environment's Docker image dies off, and then the pipeline continues on to say, let's do a deploy into dev. It will do so using a new Docker agent, a new Jenkins agent, that this time it has an IAM policy that allows it to operate in just that singular environment. So this means that if Jenkins says, do a deploy of dev, it has to explicitly announce who is able to do that deployment of dev, which agent. And so it'll, in the Jenkins file itself, when it has its node declaration, it will say, I want to use the ES microservices dev AWS environments to do this deploy, and so it'll run the Terraform code on that particular Jenkins agent. This means we can't accidentally do a deploy into staging or prod or anything else. We know explicitly what's going to happen every time, and there's no way that this could accidentally go wrong aside from we changed our Jenkins file itself. So the secret sauce to our Jenkins environment is making sure that you track those Jenkins files really well, and that we have this ECS environment that allows us to do these deploys independently. So we can do something in a dev environment without affecting prod. We know that we're only touching dev because it's completely separate accounts, and Jenkins is only able to do those operations in that dev environment. Segregates things rather cleanly. So that's the base of our AWS environments, why we're doing what we're doing, the security segregation behind them, and kind of addressing some of the audit concerns that we had. So given that, we have some other functionality that we can add into this mix as well. Yeah? It is. So the question was, is Terraform the Jenkins agent? In our environment, yes. So the Jenkins agent itself has an IAM policy that allows it to operate in that environment. So it has rights to do things. And then we have checkout of the Terraform app itself to be able to do the deploys. So the Terraform in that environment is checking out the Terraform code that's in our Git repos, but it's being applied via the Jenkins agent. So in these accounts, we have some account, the application that's running in that account. And then we have our kind of services accounts at the site level in this case. So again, we have our autoscaler EC2 and our ECS that lives on top of that. And so as you just described, we have our, actually, okay, before we get to what we just described, so we use Zabbix for some of our monitoring stuff. So in the Zabbix framework, you typically scale out your Zabbix infrastructure using Zabbix proxies. That's what allows you to horizontally scale, so that as your infrastructure gets built out, you add more proxies. So in this case, we have applications that will depend on a Dockerized instance of a Zabbix proxy, so that they are sending all of their monitoring data to inside their VPC to a local proxy service. So there's a known interface for where they should go. That's controlled over CNAMEs and all. So it's, again, just a known interface. So the Zabbix proxy itself communicates out to the Zabbix server over SSL and so on, simplifying our firewall rules. So we don't need applications to communicate outside their own VPCs in order to get monitoring data out there. They're only sending those messages within their same VPC. In the same sort of way, we run Salt in these environments as well. At the moment, we're still experimenting with these environmental Salt masters and figuring out how we want to run them best. But in general, we're capable of running these environmental Salt masters. So that means that the stuff that runs inside of any of these accounts will communicate up to a Salt master that runs on ECS, it's a Docker image, inside that same account. And then that Salt master will communicate with the site-wide Salt master, in this case the Dublin one, in order to syndic up all the messages that we need from Salt. And then we are able to further syndic up those Salt masters to company-wide ones as well for things like security auditing and so on that we'll get into in a second. So having the individual Salt masters, the engineers who have access to these environments might only have access to the environmental Salt master or only certain privileges on the environmental Salt masters. And the advantage there is that you can limit your blast radius in case of problem. But I don't really want people to act on Salt that controls absolutely everything if they're trying to do this one query or change in dev, for, let's say, in which case they're able to operate at the lowest level they need to. So that if they were to typo their globs or something too big, too broad, we're not accidentally operating on things we didn't mean to. So that just gives us a blast radius limiting capability. All right, we have the Jenkins environment that was just described. So we have a Jenkins master that exists for the site. We have the Jenkins agents that get spun up on demand by that Jenkins master. There's not just a single Jenkins agent. They're spun up on demand and per purpose. We have some logging stuff that we're doing in order to get logs out of there. That's not super pertinent to the point of this talk. And then because we're a big company, we have some DNS craziness because we run splits, DNS in various data centers and so on. So that also we have some weird hacks and workarounds to make DNS not ridiculous. So in general, this is how we run our AWS environments in order to solve a bunch of those kinds of problems. All right. So as described, one of the important bits that we have is just trying to solve for this design pattern kind of concept. So we have various policies that cover like our networking and security infrastructure, our compliance and our operating standards and so on. And so the goal with all of this is to make sure that we have a well-defined interface that makes it easy to do the right thing. So as mentioned on the previous slide, well, we want to make sure that we have stuff monitored. We want to make sure that we have stuff logged. We have logging requirements which we're required to retain all logs for at least a year, and then all audit logs potentially longer. So when an auditor comes in, they can say, show me all of your logs from October of last year or whatever, and we're still beholden to be able to display those logs. And so I don't really care if a development team writes their own logging infrastructure. If they really want to take that on, that's really awesome for them. But I also want to make it really easy for them to not have to. So I'm not interested in blocking people from doing a ton of work, but they shouldn't have to do a ton of work if we do our jobs right. And so the goal with all of this is to have a design pattern that encourages people to do it the easy way, the right way, the first time. So in our case, that means have a solution that defines your logging, have a solution that defines your monitoring, and so on. So that way, as an application team gets spun up to solve whatever business need they have to solve, they're not messing around with creating logging infrastructure as well. All right, so monitoring integration. Now we're getting past the background into how we're actually doing some stuff with Salt. So the Salt event bus is really helpful for all the stuff that we're trying to do here. So in our environments, we have this idea that any states which do something that might need to be monitored should effectively broadcast, I have a thing that needs to be monitored. So in our environment, that means that we can do something kind of like this, where we set a grain on the host where that thing is being done. So if we're installing, say, Apache on a host, we want to make sure that Apache is being monitored. The Salt state itself will set up Apache in a way that is compliant with our monitoring standards. And then we need to somehow notify the monitoring system that Apache exists and that it's in that state. And we're doing so by this example, by creating a grain called monitoring_groups. It will have a bunch of lists under it, and we will add in the Apache states to say, Apache's on this host. In addition to that, if it's some Linux host, we'll do the same thing and say, this is a Linux host. We have NTP, and so on. Everything that could possibly monitor on that host gets added to a grain that announces that it's capable of being monitored for that item. So as part of the high state, we then raise an event that says that something here has changed. So in our case, this means that we can do an event.send. We are monitoring for any changes of that grain. Whenever that grain gets changed, we have two processes kicked off here. One that raises a mine update to broadcast the values of that grain with the latest changes, and one that will then broadcast a custom event that in this case is dnb/monitoring/group change, and it passes some information about what we're doing there. The specifics of that aren't super important, but the gist here is that we're doing event.send with some grain name whenever, or with some event name whenever a grain gets updated. So any state doesn't really have to care about what happens after this. The states themselves are reasonably simple, again, trying to create an interface between the various teams here to say, if you add a grain, if you wrote the Apache state, then just make sure that you write the thing that add that grain into the grain's value into this grain, and you're all set. That should therefore get monitored thereafter. So great, we are broadcasting an event whenever this monitoring group's grain gets updated. We then have to do something with it, and that's where reactors come in. So a reactor on our Salt master notices that thing got updated. It notices that event came in, and so it will call an orchestrate job. You can have a reactor take action itself and then do some stuff, but the reactor is in the same threaded process as everything else, and so it's generally considered to be best practice to kick off an orchestrator job from a reactor to separate it out into a separate process. So in our case, we have this orchestration job get kicked off, and the orchestration job then does some stuff. In our case, it's going to look up some values that it needs to look up about the information that was in that mine and so on. Eventually, there was some talk, by the way, of Salt incorporating a slots component so that you could run something in a state, save that value within the state run, and then later use that same value. That doesn't yet exist. And so since it doesn't yet exist, we're kind of working around that by using this mine. So we're exporting the values of that grain, that monitoring group's grain, and then in this orchestrate job, we're looking up the values from that mine. Anyway, the results here are that we are running a ensure everything's being monitored properly on our Zabbix server state on the Zabbix server. We're passing along some information to do so. And then that run ensure everything is in the appropriate state on the Zabbix server looks something like this, where not that you guys necessarily care about Zabbix a whole ton, but we're creating the host groups for Zabbix. We're ensuring that the host is in Zabbix appropriately with the proxy information, the IPs, and so on. And then finally, ensuring that all the templates that were in that grain are actually being assigned via Zabbix. So the end goal here is that Apache, the please monitor Apache grain value got added to a grain that ended up broadcast on the event bus, and then Salt took the appropriate action to tell the Zabbix server, hey, make sure that thing is being monitored properly. Yeah? So the question was around if Zabbix can discover the host, and yes, it can. But personally, I hate that. That I need my infrastructure to be declarative, where if I were to say nmap scan my environment and see that I'm running Apache on 28 servers or 2,800 servers, should it be? I don't know. And so rather than depend on scanning of infrastructure to know if it should exist, our monitoring is also used as kind of a terrible unit test of infrastructure itself. So that if we said Zabbix should be installed and that we're telling Zabbix that it should be installed and should be there, if it's not, I need Zabbix to tell me. I need to see some red lights on a dashboard in order for it to get fixed. I need tickets to get opened about that. If something is installed and it shouldn't be, that's why we have security scans being run as well, but that would also be the kind of thing we need to know about. So rather than have Zabbix just say, everything's good, I discovered it all, it's, I think, way better for us to be able to say, this is what it should be, tell me if it's not in that state. All right, so monitoring, yeah?
What did you do about all your legacy systems?
Whew. So I started this off by saying we're a big company, done a bunch of stuff for a long time.
Slowly?
Yep, so slowly working them into the fold. So right now we have a lot of stuff that's in self-hosted data centers in various locations. The infrastructure in those data centers is being migrated to AWS. As we perform those migrations, we're doing stuff like this. For all of the existing infrastructure, it's not burning down yet. We have the same process that we had yesterday. So working through it one little thing at a time.
That sounds like something to take.
Oh, totally. Yeah, no, I mean, if it were awesome, we wouldn't be doing this. Like, if we were done. So it's being monitored, but in our environment involves like lots of outsourced contractors and so on who have various levels of responsibility. So it's there. People are managing and monitoring it and maintaining it, but we could just improve the process a little bit. So as we deploy new stuff, we have new process idea.
How do we decommission Apache from using this way?
So I will get into that in a couple of slides here. Sorry, how do we decommission Apache? So if the host goes away, how do we remove it from monitoring? In the case of grains, that's potentially a kind of scary thing because states will add grains. The lack of the state adding grain does not remove a grain. And so while we could potentially flush the grain at the top of the highest state and then have everything run it, that's a little scary because then you're depending on changes. You expect to have changes in your environment, so I don't want to deal with that. So we have a separate process for doing the infrastructure cleanup for the whole lifecycle. All right, so AWS integration. Sorry to start touching on this. Yeah? So the question was around the Zabbix templating side of it. So separate process, but yes, we have Zabbix templates created for virtually all of our stuff. The idea there is that if we have, say, the Apache state being created, that we'll also have that team responsible for ensuring that that's capable of being monitored. So we'll have the server status URL be allowed to be hit from localhost or whatever, add in the appropriate stuff to check that URL, and ensure Zabbix knows about all of that. So anything that is added to the system should already have the Zabbix template in place. That's part of the scheme itself. Cool. All right, so AWS-y stuff. What do we got? All right, so in our environments, we are adding minions, not with the FQDN of the minion, but for AWS environments, we're doing it with the instance ID. That was just for our own sanity so that we didn't have to worry about what IP addresses are in a dynamically changing IP environment. It's a whole lot easier for us to track instance IDs generally, so not a big deal, but just a quick recommendation of that makes stuff a little bit easier sometimes, so why not? In this case, we're falling back to host name if the metadata isn't look upable. All right, so we're also using some custom grains about stuff. So in our environments, because we have multiple accounts for each of these things, we're capable of treating these things a little bit differently. So we can do something like for an instance that has an EC2, so there's a custom grain that allows you to look up the metadata on a host from an AWS environment, or actually Azure and a bunch of other things. And so that custom grain exists in our environment. So that custom grain creates a grain called EC2, underneath which is all of your metadata about that EC2 instance that's available to it. That's generally lookupable, so that's pretty easy. We can use some of that data then to make decisions on later, which makes it a bit easier to run in AWS. Because we have multiple AWS accounts, we can then treat these things in different AWS accounts differently. So if your account ID is all 9s, then run this thing on it, or whatever you need to do in that environment. Likewise, there is also a custom grain that's able to look up the roles of the machine based on tags. So in our case, we have a custom EC2 tags grain that will, we have a policy set that any host has to be able to look up its own tag information in order to make this function. And so any individual instance will look up its own tags using Bodo libraries. Those tags are then broadcast out as grains. And then there's a special one for if you have a tag named roles, that it will then populate a list item that allows you to then look up that stuff. So at the very beginning of all this, I mentioned in our AWS environments, we provision with Terraform. Terraform's responsible for ensuring everything's tagged properly. This is why. And so that by having a development environment, if you say this is a whatever microservices dev Tomcat instance, we can have a state that's, and you tag it as such, as a role of this is the role that this machine is going to do in AWS. We can then, based on those tags, have Salt provision it to do the right thing. Question?
So grains, I don't consider to be secure.
You are totally right.
So what do you do about that?
So we've been investigating migrating this grain that looks up tags and delegating that to an external pillar and having the Salt master do it itself, in which case that would resolve that problem. And so that's kind of in process right now. We're seeing if that works. So far, so good. Grains, so the question was around, our grains generally aren't super secure. Yep. Anyone who has roots on the instance is able to add grains, in which case you could potentially pretend to be something that you're not if you actually rely on grain information to do some stuff. That will come up again in a second. But in this case, we're capable of migrating this grain information to a pillar, but also the teams that are working on these environments are the teams that are managing these environments. So it's actually not that big of a security risk because the same people already have root anyway. All right. And then we get back to lifecycle management. So this is the thing that was referenced earlier about how do we clean up anything. And so one of the cool things about Salt is that it has this idea called engines. Engines are long-running processes that run on the Salt master, or actually minions now as well. But you can have an engine do something. And so there's already an engine that can talk to an SQS queue, and there's an AWS concept as part of the config environment where you can say, upon instance termination, broadcast that instance terminate event to an SQS queue. Those two things combined allow you to have AWS send a message whenever an instance gets terminated, have Salt monitor that SQS queue to pick up those messages and to see it. The engine then rebroadcasts that event from the SQS onto the Salt event bus, which allows you to create a reactor which can then do something based on the termination of that environment, or of that instance. So in this case, we can message, our office uses Microsoft Teams, so we're sending a message to Teams to say, hey, this thing got killed off or whatever, just so everyone's aware, doing the whole chat-opsy thing. But we can also say, delete that minion's key from the Salt master, because we know it went away. We can clean it up from Zabbix, we can remove it from AD, whatever it is that matters in our environment for that instance. So lifecycle stuff, super important. All right. And then we have some collaboration-y bits. So in our environments, we have a Salt master. Makes sense. The Salt master pulls in states from a Git repo. It pulls in pillars from another Git repo, and so on. So we can do things like spin up a minion and apply some stuff to it, where that minion, let's say, installs Apache, and then pulls the information from the pillar in order to provision that Apache instance as directed. Cool, everything makes sense. I mentioned that we had the multiple salt master capability here, so we can share those same salt states amongst many teams and many locations. So the way that we operate, for example, we have offices in Malibu, Austin, Short Hills, Dublin, a bunch of places, in which case each of those local development centers might have their own salt master with the multiple salt masters underneath them as appropriate. But we can share the salt states between them all because they're all in Git repos. We can share the ownership of those states and so on. We can have those states validated by the security team once, instead of having to have the security team check out every office's instance of that thing. But we can also override those pillars as necessary on a local level. And so in this case, if in Dublin we want to override threads from 2 to 4, we can do so. And thus, when we provision a host off the Dublin salt master, we can then say, great, you get the same Apache state, but we're going to change around some of your configs. The salt environment, the salt method for doing pillar overriding isn't super advanced. So we've investigated a couple of things here. I'm not sure that we found the perfect solution yet, but we are investigating using the external Git pillars and just ordering them by having the Dublin one be later in the lineup than the earlier ones, in which case it overrides by default. But then you get into a situation where you don't necessarily always want to override. And so for that, we've been investigating. There's a concept called, was it pillar stack? My mind's blanking now. But there was a guy, an external contributor, who wrote a method for doing, defining what pillar events, or what pillar values can override other pillars, and defining the logic by which that can happen. I believe that was called something stack. Was it pillar stack? Was it? Value stack? Not sure. Pillar stack? And then there was another guy who recently plumbed all that up into Git, so that in the same way that we're doing GitFS for management of our environments, there's now a Git stack, which merely adds in the Git checkout capability on top of pillar stack, which now makes it like actually really useful. So that's the currently in investigation. All right. And then, as promised a little while ago, we have an environment here where we have Dublin runs a salt master with some stuff underneath it. Well, we also have Malibu runs a thing. We have this other group called CloudOps, they run a thing, and so on. But our security teams would really like to know what's going on in our environments. They don't want to have to ask each of our like local owners to figure out what's going on. And so we have a question to ask. Who's running what version of OpenSSH? Or sorry, what version of OpenSSL? So in that case, we can run a salt master on top of everything. We could tie these things all together with Syndic, and thus we can run a query on a top-level salt master, have it ask down, have all those guys report up their answers and so on, and get back some results. And so in this way, we're capable of leveraging Salt for what it's really good at, which is slightly greater than just pure configuration management, but on remote execution in order to be a CMDB-like operation. We're capable of getting some of these questions answered, and because we can also manage the kind of access controls over what these top-level salt masters are doing, we can delegate to some level that the security team is able to run these queries, and just these queries, they're not actually just installing stuff or messing around with development environments directly. So pretty useful. All right. So Jenkins also plays a role in all of this as well. So I mentioned Jenkins for doing our AWS provisioning, for our CI pipelines and so on, but it actually ends up being a little bit helpful for other bits as well. So we had a use case of before doing this, we had Jenkins that would actually SSH onto servers and then run some shell script stuff to deploy apps, which is not awesome. Don't recommend that. If you're in a data center where like your IPs never change, it's not great, it's stupid, but yeah, you can. If you're in AWS, you just can't, so it's just insane. And so as a method of doing something better, we've been moving a bunch of those deployment tasks to Salt, and that's helped us out quite a bit because it's way less crazy, and that now means that people don't have to, the way that Jenkins was previously doing this, people would go into Jenkins, they'd create a job to do a deploy, they would add a build step into that job, and then they would type some stuff into a web page. As mentioned at the very beginning of this, I really like that stuff is tracked in Git because we can track it. And so if you don't have tracking on something, you don't know what's going on. Who modified that Jenkins operation? I don't know. If we migrate this stuff onto Salt, we now have much more authority to figure out what's going on in our environments. We end up with change controls and tracking, commit messages. We can see who did it and so on. So when we did that, this also allows us to tie Jenkins into Salt. As mentioned, we have this Jenkins Salt plugin doodad. It supports Jenkins pipelines. And so here's a little pipeline snippet to run a Salt state on a host. So in this case, It's going to run the deploy advanced monitoring job on our host and so on. And so we're able to like run those things from Jenkins. So it's just a line of doing that thing and then all the logic that entails what that thing actually needs to do is incorporated into Salt, which is a much more sane operation rather than our previous SSH shell scripty thing. Likewise, we also had a use case where our data centers are not exposed to the public internet. You can't get out from a data center. So this is, again, some capital E enterprise stuff. And so what we did around this was we really wanted to like know when a deploy happened. We wanted Jenkins to be able to tell us, but Jenkins isn't able to message Slack. So that got really obnoxious. And so we, again, leveraged Salt to say, run a hook. So the Salt API has a hook function, which allows you to broadcast an event on the Salt event bus. So rather than running a state itself, we are saying, hey, Jenkins, just broadcast this message on the event bus. This message is that the advanced monitoring build was deployed to a certain event bus ID. And then the Salt master itself has a reactor that then will take that message and broadcast it to Slack because our Salt environment does have internet accessibility and thus is able to message Slack. So in that way, we were able to work around our messaging issues based on IP availability. All right. And moving through this, secret stuff. So we've been using Vault. And as of the 2017 release, the Vault modules for Salt were drastically improved. That was also done by an external contributor, where when we were investigating what we were going to do about secrets management, we were looking for stuff, we found this guy's thing, and then pinged him and went, hey, it looks like you're done, and this thing's pretty awesome. Do you want to contribute that back to Salt or anything? Like, is it ready? Are you able to use it? And the guy replied to us and went like, oh yeah, no, totally. We've been using it for years. I forgot that it wasn't in upstream yet. I'll upstream it now. And that made it into 2017. So just to walk through what Vault is really fast, it's a REST interface. It's a reasonably dumb, pretty simple REST interface. And so we can have a client out there that communicates with our Vault server, and the Vault server over HTTPS. The Vault server itself saves its data on this console backend. It does so based in an encrypted format. So at no points in the wire is something happening in an unencrypted channel. That's kind of Vault's thing. So great. We have an encrypted mechanism. We have a mechanism for talking to this service over an encrypted channel. That's pretty cool. And so the use case that we have for all of this is I want to have a Git repo that does not have passwords in it. So currently, we have probably some usernames and passwords in text files that are in Git repos. Anyone who has access to that Git repo can read our username and password, and that's terrible. So as a fix for that, we could just plumb up Vault. So we could save that user and password and put it into Vault. And that's pretty cool. The way Vault accesses its secrets, though, you have a token. So that token has, you basically creates a short-lived token. That short-lived token has a policy that allows it to read or not the various endpoints in the REST interface. And so if you have a secret that exists at a certain endpoint, you can create a token which is allowed to read that secret. So cool. I could replace my user and password in my Git repo with a HTTP lookup to Vault and then put my token in there. So I haven't really solved that problem because now whoever has access to my Git repo can now read my token and just do the lookup themselves, which is kind of the same problem. And that's still pretty terrible. So there's other ways of working around that. But because we have Salt in our environments, it's actually way simpler. So the way the new Salt modules work, we have a minion out here that needs to access a secret that's kept in Vault. And so rather than having that minion directly communicate with Vault and needing that token at all, we can instead say, minion, please run the Vault module to say, read a secret. That will cause our minion to reach out to the Salt master and say, hey, I want to read the secret thing. That happens over an encrypted channel because it's Salt and it's all pretty good. The Salt master itself at this point has a configuration applied to it where it has its own token. Only the Salt master's token is able to generate new tokens and only do that activity. It can't actually read any secrets itself. So this means that our Salt master, knowing who that host is, can now request a single use token from the Vault server. And when it makes that request, it can request certain policies to be applied based on information about that host. So we can do so based on pillar information from the host or grain information from the host. At the moment, back to the grains aren't super secure thing, this is actually really crazy because if you end up with Vault lookups in pillars, you can't enable the pillar integration here because then you end up with recursive loop. And so either you use pillars or not, and you have to make some determinations. But the short of it is that because Salt knows who's requesting this and what roles and so on are being applied, that allows you to create policies that do things like all MySQL servers can access this secret, or only the MySQL server in this one environment can access it, or this one minion ID is able to access it, kind of whatever you need. And so in that way, we get this token management, that token management thing that was previously a really big problem, we kind of just solved for free with Salt. And so with that, the Vault server now replies back to the Salt master now replies back to the host, the host uses its single-use token to connect to Vault to get back its secret. Yeah?
Okay. Awesome. Excellent. What do you do about the event bus and it logging all that stuff gets sent all over?
It does not log the token IDs.
Okay.
So yeah, that should be A-OK.
Okay.
They're passed through another channel other than the event bus.
Did you have to integrate with any existing secrets vaults?
We were doing this more or less from scratch, so no. But there's no harm in doing so because it really comes down to those policies. So if you have a policy that, as long as you can assign that host a policy, that's the mapping that Salt needs to know about. Otherwise, you're pretty good. So by default, you'd probably roll it out slowly where you kind of give everyone no rights to anything and then slowly deploy out what you need as you are able to write your Salt templates to then use these vault.read secret lookups. Yeah?
Can you explain how an execution module running on host 1, mid-execution communicates with the master for this entire workflow to work?
That is all that it does. So the execution module calls some util function. The util function sends a message to the Salt master purely for this communication. That is written specifically for this one task.
This is not part of the standard things that you do in execution module.
Right. Yeah. Slightly weird use case here, but it's totally rocket. So you basically get secret management for free if you guys use Salt, with Vault. So that solves a bunch of problems. As mentioned, the real secret here is just defining those mappings for what your policy should be, and also making sure that you use pillars where appropriate, because as mentioned, if I had an instance of this host where someone had root on it, they were able to add their own grains. Because they're able to add their own grains, if I said all MySQL servers in this environment can read a secret, well, that host, if you had access to the grains, you could just say, I'm a MySQL server too, and then perform these lookups. So that part's not great. That's like, it would be really cool if we had a method of determining pillar recursion. So we'll see what that gets solved in the near future. But in short, it's capable of working pretty well. So great. So that's useful for secrets generally. So that allows you to create a Jinja template where you say the value of this variable comes from that vault.read secret lookup, and it all kind of just works. But it's also useful for things like Jenkins. So as mentioned, Jenkins does a bunch of stuff in our environment. And so we provision out our Jenkins server from Salt itself. So to do that, you have your standard use where you install Jenkins, and that's pretty good. And you have to install the plugins that Jenkins is going to use, and that's pretty good too. But there's also a concept that Jenkins has of credentials, which are saved in Jenkins' own secret store. Some Jenkins environments, some plugins allow you to look up secrets from somewhere else, and maybe that's useful. But at the end of the day, you probably are going to need to actually use a Jenkins credential to get some real work done in your environments, in which case, Jenkins itself has the ability to have an init.d directory that it will read all of the Groovy scripts inside on startup. So the way that we're doing our Jenkins install is that we're installing Jenkins, and that part's pretty good. We can install plugins and say install the Active Directory plugin, for example, so that it binds to our LDAP servers, and that's pretty good. But we also need to configure that Active Directory plugin. And so we do so by having a Groovy script that Salt pushes out to the Jenkins server and populates into that init.d directory that Jenkins reads. And in that way, when Jenkins starts up, it will then install plugins or whatever it has to do for the earlier Groovy files, but later Groovy files can do things like now configure those plugins themselves. So we have a zero-touch Jenkins setup in our environments now, where we can go from nothing to fully populated Jenkins server where fully populated incorporates things like Active Directory binding. To do that, by the way, we just took the existing Jenkins formula that exists out there on the SaltStack formula site, and then just found out about this init.d thing, and then added a bunch of stuff there. So we'll probably try to throw in a couple sample files or something just to get everyone started, because there's not that much to it. It turns out to be way easier. A lot of the formulas and things that interact with Jenkins either do so over the REST API or through the Jenkins CLI, and both of those interfaces are very limiting for things like configuration after the fact, in which case the Groovy script thing totally works and is a reasonably scalable way of going about things. Well, because we have that Groovy script capability now, we can do things like have Jenkins in that Groovy script say, do a bunch of Vault lookups in the same way that we were just talking about, where it asks the Vault server for the values of these various secrets and so on. Vault server replies back, and we will save those secrets as Jenkins credentials. So the end result here is that Vault is authoritative for secrets in our environment. But Jenkins itself can also have access to those as necessary to be able to use them as Jenkins credentials so that Jenkins plugins and so on can use them as appropriate. Cool. All right, so quick slide on lessons learned. You really need to define all of your interfaces between teams and your processes. That if you have unknown who's responsible for that thing problems, that's going to bite you forever. So make sure you have just some definition of what's going on. Tackle one problem at a time, go through a continuous improvement process. So not all of this stuff should be deployed all at the same time. Just tackle one problem, make it not totally stupid. A bunch of the stuff I mentioned is still kind of work in progress to some degree, so just keep it going. And that's about it. Yeah?
So you mentioned you have one Git repo where a bunch of teams have all their states in there, right? So how do you ensure that one team doesn't merge a pull request that would make another team mad and screw up all their stuff?
So that comes down to, you're talking about, the question was around having multiple Git repos managed by different teams.
I thought you had one Git repo with states that multiple teams use, or was I wrong about that?
So at the very beginning, I mentioned that we had the Git repo that had application code and Terraform code. That's managed by the application engineering team. Salt states are different places. So there's actually no crosstalk between those.
So
different
each team
problem.
has its own Salt Git repo.
Each team has their own application code repo. If they want salt states, that's managed by the DevOps engineering side of stuff, in which case those engineers are probably embedded with those development teams, and so they're talking, but they're not the same folks necessarily. That also brings up the what's your CI pipeline for testing out your salt states and so on, of which there's many talks here about that problem. Cool. Well, we've got folks walking in, so I think we're about set. Thanks, everybody.